today's topic was still momentum, but now we're talking about momentum in terms of collisions. So, again, part of the premise of last class was dealing with conservation of momentum. That no matter what is happening for an isolated system with no external forces, the momentum before has to equal the momentum after for whatever is involved in your system. So now we have interacting objects. Their momentum is going to have to be conserved. Each momentum is going to have to be conserved. And we can talk about that in terms of two different types of interactions. One, where the two objects completely bounce back from each other, and the other one where the two objects stick together. So, we have an inelastic collision, and a perfectly inelastic collision is where the two objects stick together after the collision happens. So think about two cars that might be coming together at an intersection and end up being together and moving off in one direction all together at the same speed. That would be a perfectly inelastic collision. In that situation, yes, the momentum is conserved, but the kinetic energy is not. And so, the only equation we have to worry about is the conservation of momentum. That being m1 v1I plus m2 v2I is equal to m1 v1F plus m2 v2F. Where again, m times v is momentum. Okay? Now the special thing about a perfectly inelastic collision that is where the two objects are stuck together and therefore move at the same speed together. So v1F equals v2F, which we'll just call v. So if you have perfectly inelastic for your collision, then m1 v1I plus m2 v2I is equal to m1 plus m2 times v. So we would have m1v plus m2v, and you can factor out the v, therefore. And so you have the momentum of the first initially plus the momentum of the second initially is equal to the momentum of them together at the end. So that's what happens if you have two objects that collide and stick together. You do not have conservation of energy because the energy will be lost in making those two objects go together at the same speed at the end. The other type of collision instead of inelastic is just elastic, where just like with rubber being elastic or other things that stretch and bounce are elastic, you have two objects that bounce off of each other. They do not stick together. And in that situation, you have momentum being conserved, and kinetic energy is conserved. Nothing happens during the collision to take energy out of the system, unlike in the inelastic collision, where during that collision energy is lost. For an elastic collision, the kinetic energy stays in the system, and it's all there, it's all conserved. So we not only have momentum being conserved, we also have the kinetic energy being conserved. Okay, so the initial kinetic energy for both of them together is going to be equal to the final kinetic energy of both of them together as well. And the initial momentum for the two of them has to give you the momentum at the end. Okay? And you can use both of these equations. You do have to use both of these equations when you're actually figuring out what's going on for these types of specific examples. But you also can get a simpler equation by relating these two things. Okay? And the way you do that, as I did this in class, is you get all the n1s on one side on this equation, all the n2s on one side on that equation, and you see what you end up with for your answer. And what you realize, and when you relate this to this, and if you want to try this again without me doing it for you on the board, that would be a good exercise to do, to solve for this and factor it out, and then see how that compares to this one, you end up with V1I plus V1F is equal to V2I plus V2F. Or V1I minus V2I is equal to V2F minus V1F, which also says V1I minus V2I is equal to negative V1F minus V2F. So when you relate these things, the masses will go away, and you're just going to be dealing with one power of the velocity. So that's the magic of the algebra, not the magic, the beauty of the algebra that comes through that lets you make this simpler statement. That is a true statement based off of these two things. And what it says is that the velocity difference between the two things at the beginning is equal to the velocity difference of the two of them at the end with a negative sign. So, if one of them has, well, I won't go into a specific example making up numbers off the top of my head, but that's what's happening, is that you have the two objects that have a difference in velocity to start with, and at the end, that difference has to be equal to the difference of the final velocities, but in the different direction. That's what the negative means, right? In a one-dimensional thing, we have positive and we have negative for our two different ways something could be going. All right. So again, this only applies if we have an elastic collision. This does not apply if we have an inelastic collision, because it came from this, and this only works if you have an elastic collision. An inelastic only conserves momentum. An elastic conserves both momentum and energy. Alright, so speaking of directions and dimensions, so far we've only talked about collisions in one dimension. However, we do need to talk about them in terms of two dimensions. And so we refer to glancing collisions as the very first example to talk about this, where instead of having two things hit head-on, you have one hit slightly above the other. So if you play pool, if you play billiards, then you can think about the example of two different balls, two different pool balls that are going to be hitting each other. Instead of hitting head-on, they're going to be hitting slightly off, and so they will go in whatever desired direction you hopefully wanted them to go for your shot. But they will definitely go in different directions, based on how that collision happened. Okay? Or if you have two things that are traveling in different ways, and not the same dimension, and come together, then the resulting movement is going to be based off of two dimensions as well. So if we just first talk about glancing collisions, where we have some object hitting another object, but not head-on, then the resulting movement of these two things will be one object going this way, the initial one, which I'll call 1, and this one I'll call 2. Then they're going to be going in this direction after they hit. So this is like right when they hit, and this is after they hit. This one will be moving at an angle phi from the horizontal. This one will be black 2. And this one will be moving at an angle theta with the horizontal. And so we talked about in class how we need to be able to conserve momentum from each situation. You have to look at conservation momentum in both the x and conservation momentum in the y. Each one is independently conserved. In the y direction here, we have nothing to start with. It has 0 initial y momentum, because everything, the second ball is sitting there at rest, and the first ball is coming in straight across in the x. So it has 0 y momentum to begin with. So afterwards, it has to have 0 y momentum as well. So let's look at that. So y, looking in the y direction here, we have m1 v1 I y plus m2 v2 I y is equal to m1 v1 I v1 f y plus m2 v2fy. So these are both 0, as I said before. And now we have m1v1fy and m2v2fy, and we can look at these angles and look at the general overall v1f and v2f and express it in terms of that. So we want to write m1 times v1f sine theta plus m2 v2f sine phi. Because the sine is going to be giving us the right dimension for that velocity. Because we want to look at the y velocity, which is in this picture, is the up and down part. And so we would need the part across from the angle, or opposite the angle, therefore being the sine trig function for the one we want to use. So these two things are 0. We have 0 equals m1 v1f sine theta plus m2 v2f sine phi. We know that those two things have to be equal and opposite because there's no y momentum to start with. Okay. So looking in the x, we would have m1 v1 I x plus m2 v2 I x is equal to m2 v2 well, let me start with 1. m1 v1 f x plus m2 v2 f x. And yes, things can get a little bit messy with your subscripts. You have to be very careful that you stay consistent with your subscripts. So in this situation, it's not the second ball is not moving. It's at rest. Okay, so that's gone. So we only have this direction for the initial one. So that's just going to be vi. And we have these two, which have to be broken down into their components. So we have m1 v1 I x is equal to m1 v1 f cosine theta plus m2 v2 f cosine phi. So you have to look at the x momentum before and after. It's got some before, so it has to have something after. And so these two things right here are not going to be equal and opposite because it had some to start with, and so that number has to be present at the end as well. Okay. There's one more thing that we can look at if we assume this is an elastic collision, and that, if you remember, is the conservation of energy, the conservation of kinetic energy. Okay. And you do not break down kinetic energy into components because it's just a scalar. Energy is a scalar, not a vector. Momentum, however, is a vector because it's based on just the velocity. The kinetic energy has a velocity squared, and therefore it is not a vector, it is just a scalar. And so you only need one equation for that, not two. So it would be 1/2 of the initial block's mass, of initial ball's mass, times this velocity squared, plus 0, because this object is not involved in the initial energy because it's at rest. And that equals the final kinetic energy of this one, plus the final kinetic energy of that one. So that would be, if I were writing it here, Ke, we have 1/2 m1 v1 squared equals 1/2 m1 v1 f squared plus 1/2 m2 v2f squared, where the angles are not involved because we want the whole velocity along that line. Okay, so that is how you would approach these types of problems. If you have some kind of collision in 2 dimensions, you need to look at both the x component and the y component. And then you have to know, separately from that, if the situation is elastic or inelastic. If it is elastic, then kinetic energy is conserved. If it is inelastic, then kinetic energy is not conserved. So that's how you'd be approaching these ideas, still using our idea of the conservation of momentum, which is where all this is based off of.